So good morning, everyone. I think we should continue in this conference, even though some people are still coming in. I'd like to welcome you to this next session of this Thorium conference, and it's actually already session number 9. This session is devoted to accelerator-driven systems, so that's the combination of a high-power accelerator and a reactor. My name is Mike Seidel. I'm working at PSI at the Paul Scherrer Institute, and at this institute I take responsibility for the operation of a high-intensity proton accelerator that we actually use to drive a neutron source. And actually, there are only 2 accelerators in the world, ours and another one is the spallation neutron source in the US in Oak Ridge, which can go beyond 1 megawatt in beam power. So that's my expertise in accelerators, and I guess therefore I have been asked to chair this session. So in this session we will have 5 presentations. They are all devoted to accelerators, and the first of it will be given by Jean-Pierre Revol. He will give us an introduction about the ADS concept, about ADS physics and motivation. You know him already very well. He takes a lot of responsibility for the organization of this workshop. So please, Jean-Pierre.
Thank you very much, Mike. Since this is the first talk on ADS, I will start with a very brief historical account of ADS. Then I will discuss thorium core physics. Actually, since we're at CERN, I think it's a good idea to discuss physics. You will not learn anything new about this physics. It's very well known, but there are people who don't seem to know it, or others who seem to have forgotten it. So I think it's worthwhile to talk about physics. I will make a few comments about accelerators. Right after my talk, there will be several presentations on accelerators and a few general statements about motivations and global constraints. The basic process in ADS is nuclear transmutation. In fact, the first accelerator was simply polonium-210, and Rutherford used it to transmute nitrogen into oxygen. In 1940 is the proposal to use a particle accelerator as a neutron source. Seaborg produced the first microgram of plutonium with the cyclotron. And in 1950, Lawrence proposed the famous materials testing accelerator at the Lawrence Livermore Radiation Lab. The idea at that time was to produce plutonium from using Oak Ridge depleted uranium. In 1952, Lewis in Canada proposed to use also an accelerator to produce, in this case, U-233 from thorium, which they wanted to use in CANDU reactors. Now, for a number of reasons, both projects were dropped. I think one of the main reasons is at that time uranium ore deposits were found in the US, and it was also realized that in order to achieve what they wanted to do, they needed several hundred milliamps of beam intensity, hundreds of megawatt of beam power. At that time, their system had no amplification and so forth, and simply the accelerator technology was not ready. Today we know we can do those kind of things with a much more modest accelerator. 10 megawatt is more than sufficient, and you can do a lot of things with less than 10 megawatt. There was a renewed interest in ADS in the 1980s when the USA decided to slow the development of fast critical reactor, the fast flux test facility, which eventually got closed completely in 1993. So you have a proposal by Takahashi at Brookhaven National Lab. He proposed burning actinides in a system with the K of 0.99. Bowman at Los Alamos proposed a thermal neutron ADS. They called it Accelerator Transmutation of Waste, ATW, with thorium and chemistry online. That's essentially directly related to the MSR idea. And Japan launched the Omega project. Well, in the 1990s, Carlo Rubbia gave a major push to the field by launching a vigorous research program based on several elements. First, innovative simulations. Nowadays, you have MCPX and so forth. Everything works well, but I can tell you at that time that was not the case, and Rubbia and his group developed a really innovative simulation at the time, including physics from the proton beam, the spallation physics, and then the core physics. He conducted 2 experiments at CERN, ThEC and ThEC. I will say a few things about that to validate the simulation. And you heard a beautiful talk this morning on NTOF, which is also part of this whole effort, because in order to simulate something, you need to have good input data. And he also proposed a couple of demonstrators, one to the European Union, the other one developed in Italy. Anyway, I think Carlo Rubbia is probably the main reason we are all here discussing this subject today. So the basic elements of an ADS system are a particle accelerator to provide a neutron source, a core in which a neutron and fission, source neutron and fission neutron are at work together. You can see here the energy spectra of fission neutrons and spallation neutrons. You see they are not very different. Spallation neutrons are harder. In fact, there is a high energy tails, which is not negligible. It counts for a non-negligible part of the neutrons, and in that tail there is even non-fission multiplication because of n-xn reactions. So there are basically two main areas of physics in this field. There is the physics of the neutron production by spallation, produced by, in this case, protons on lead, and the physics of the neutron transport and interaction in the core. Of course, physics enters all the elements of the system. The cooling physics also is the thing that determines natural convection, if you want that. Electric power physics also is giving you some constraints. If you want to maximize the efficiency for converting heat into electricity, you have to remember the Carnot cycle and remember that you want to work at the highest possible temperature, and this is one of the things that people are trying to achieve. Of course, you know, the real system are a little bit more complicated than the thing that I just showed. You see here on the left the energy amplifier proposed by Carlo Rubbia. You can see here maybe one of the first prototype proposed to the European Commission in 1999, which was engineering design by the Ansaldo company. You see here the new Acre solution that Carlo mentioned in his talk on Monday, which is also a little bit more sophisticated than the sketch. However, the point is that today one can simulate in great detail any realistic system. And remind you that in the LHC experiments at CERN, people simulate very complex detectors. They have up to 30 million volume elements in their simulation. So that means that you can, in principle, simulate those things in great details. The basic physics is extremely well known. Of course, the issue is to get good input data, and you heard already something about that. And remember that a simulation is never better than the quality of the input data. So, even though you cannot simulate anything without doing a real complete job, I think it's possible to get some kind of insight in the physics of those systems by simplifying a little bit the model. And it's quite interesting in itself to look at the physics of subcritical systems. I mean, this physics was worked out in particular by Rubbia et al. in several notes here that you can find on the web. So the knowledge of the neutron flux geometry actually is important in those systems because it determines the generated power distribution and the uniformity of burnup and things like that. So if you simplify things a lot, you take a uniform material, monoenergetic neutrons, small absorption, then you can get a relatively simple equation where you have the variation of the density of neutrons, which is a balance between production and loss of neutron and absorption. So you have fission term, and in a subcritical system, you have a new term which represents the external source of neutrons. So if you want to look at what happens at equilibrium, then you get this type of equation, which is well known. I will not go into these details here, but just note this term, k infinity minus 1. And the interesting feature is that depending on the relative value of k infinity with respect to 1, you get different types of solution. If k infinity is smaller than 1, which was the case actually in the FIT experiment, then the solution is exponential. If k infinity is larger than 1, then the solution is oscillatory. In fact, it's more favorable if you want to have a more uniform distribution of your flux. So you get very different types of solutions. You know, the standard way of resolving this thing is that you first get the eigen functions of this thing, and then you can expand the source over these eigen functions, and then you get the answer that you want. You get the flux, where you see a sum over all these eigen functions, which are all the modes which you actually excite with the source. In a critical system, only the fundamental mode is there. In the subcritical system, all the modes are there, and they're each amplified by a factor 1 over 1 minus k. And this k changes with the mode. And you can see very easily that since this KLMN is k infinity minus something like this, where these are the eigenvalues of these systems, and they increase with the increasing mode, then these k's decrease, and that means there is less and less amplification as you go to a higher and higher mode, and you get a very nice theorem is that if the fundamental mode is subcritical, then all the other modes will also be subcritical, which is a good thing to have if you want to build a system like this. So the physics is fun. You can look at the time dependence effect. For example, you can look at the response of this system to a delta function. You put a burst of neutron and look at what happens. And when you work out the solution, you find again this k, which is related to one mode, and this 1 minus k factor becomes larger and larger as k becomes smaller and smaller, which means that the characteristic decay time is shorter as modes become higher. Of course, at the critical limit, these terms become 0, and then the mode is infinite. And that is something which is very interesting, and this is actually something that Fermi used when he approached criticality in his first pile in Chicago in 1942. He looked at the time, the time of the neutron burst in the system. Of course, this is a very nice feature that can be used in ADS system. You have an accelerator, and you can make little interruptions in the beam and study this and measure those Ks very precisely. Now let's look at neutron multiplication. So in a system without a source, you can define an effective K, which is the ratio between neutron production and absorption and leakage. And of course, if you go to a fast system, you have to do things a little bit more sophisticated because you have a non-fission multiplication due to NXN reactions and so forth. However, you can see that this K gets modified significantly if you add a source term. And the source term is positive, so that means the K with the source is different from the K without the source. And it's actually a very nice feature because if you adjust your K source to be let's say 0.98 as in the energy amplifier, as soon as you switch the beam, your K moves to K effective, which is smaller. And this is a very nice feature, which is not always known to everyone. Well, in ADS systems, you can look at what happens when you produce a certain number of neutrons with the source. You get generations like in any other system, but because your K is smaller than 1, there is a limited number of terms that can contribute significantly. For example, with the K of 0.98, after 1,000 generation, you need N0 of 1 billion neutrons to have 1 left after 1,000 generations. So that decreases very quickly. And then you can work a little bit the mathematics to get this amplification factor by 1 over 1 minus K. So you can define an energy gain, which is the ratio between the energy produced in the EA divided by the energy injected by the beam. So it's fissions at work, so you get 180 MeV of kinetic energy from fission. You need the number of neutrons per proton, you need the number of neutrons per fission, and you need the beam energy, and then you get this type of G0 Ks over 1 minus Ks, which if K is large enough is about equivalent to this. And it's interesting to see that when you do the real simulation or when you measure those things as we did in the ThEC experiment, then you get a value which is very close to what you expect, even with this simple-minded type of approach. And the characteristic constant G0 depends on the nature of the target. You get G0 equals about 3 for uranium, 2.7 for lead, etc. It's characteristics of the target. So those things were actually measured in the ThEC experiment in 1994. It used a small assembly of natural uranium, which was actually used in Spain in a nuclear engineering school to teach students how to measure K. And it was brought to CERN, adapted to a beam. You see the PS beam here. And in fact, it's our late friend Antonio Rubio who contributed this. He's unfortunately no longer with us today. But this was a very nice and simple experiment. You either count fissions or measure temperature, and then you find out what happens. And as I told you, this was a system with a K infinity smaller than 1, so you expect an exponential solution, and this is exactly what you find. And you know that's to be compared to the distribution you would have if you were dealing with a critical system. The key point of ThEC was to measure the energy gain versus the kinetic energy of the beam, and you can see that you have a region below 1 GeV where the gain rises, and then there is a plateau. At low energy, protons use a lot of their energy through ionization, so they are not very useful for producing neutrons. But as the kinetic energy increases, you make more and more nuclear cascade until you reach a saturation. If you would continue a little bit more, you would have something that comes down slowly because you start producing other types of particles, pions, and so forth. So the two things are interesting here. You can see that the simulation and the measurement agree quite well, and you can also see that already at 800, 900 MeV, you have optimum conditions, which means you certainly don't need the LHC to have the best possible ADS. At a few hundred MeV, things are there. And of course, this validated the simulation. Now, the energy gain is being understood. You can look at what beam power you need to achieve a certain power in the system. And of course, there is a trade-off between accelerator power and criticality margin. If you look here in this plot, you have the beam power versus K for various thermal power for the ADS. And you can see that as your K gets closer to 1, you need less beam power. This curve here corresponds to the energy amplifier of Carlo Rubbia, and you can see that with 0.98 you need about 12 milliamp or 12 megawatt. With 100 megawatt, you need a lot less. And in fact, if you take megapi, that is a spallation source at PSI that achieves about 1 megawatt, you can see that you can already, with a system similar to the energy amplifier, produce 100 megawatt. With 100 megawatt running for a full year, you can burn 30 kilograms of plutonium of minor actinide. So this would already be a significant system. There is one feature of the neutronics of the thorium chain which is interesting, which is a drawback in critical systems, because the lifetime of protactinium-233 is about 10 times longer than the lifetime of Neptunium-239, and that makes the breeding process a lot slower than in a uranium-plutonium system, and that's one of the problems. But this becomes an advantage for ADS, because that means the response of the system is also much slower. If you suddenly increase the power of your beam, you start burning more U-233 than the protactinium can bring immediately, and you have a response that goes over the characteristic time of 1 month, where you lose reactivity and then the reactivity goes up, and the opposite goes in the other direction. If you decrease the power of the beam, then the reactivity goes up, because suddenly you burn less U-233 than what is coming from protactinium, and then you go back to equilibrium. So this very slow response is certainly also an extremely attractive feature. So you already know all these, that thorium-232 is quite far from plutonium. In fact, if you put it in numbers, if you look at the equilibrium concentration of plutonium in a uranium-plutonium system, it's very, very small, 10 to the minus 4, as opposed to, for instance, 15% in a UPU system. So if you want to go in the incineration mode in this UPU system, you have to work with a very high plutonium concentration, while in the ADS you don't need that. All right, here we have some features of these systems. I won't have time to go, but obviously we are insensitive to the delayed neutron fraction. The reactivity changes only very slowly. The beam can be switched off very quickly. Here is the response of a critical system to an accidental reactivity insertion of $255 per second for 15 milliseconds. You can see response times of system of order 5 milliseconds. First of all, in a subcritical system like the EA, nothing much happens if you do that. And in addition, you can switch off the beam in only a few tenths of microseconds, so it's almost at 0 on this scale, which means that you also go to a lower K, 0.97 and something in this case. So this is really interesting from the point of view of safety. Now, why do we want fast neutrons is to enhance TRU fission probability. And if all TRU fission, then you don't need to separate plutonium from the rest. And in that sense, the pyroelectro reprocessing is a very good capture, a very good element of this system. Now, in a thermal system, the capture on fission products is the thing that limits your burn-up. So if you have fast neutrons, the captures are a lot less, and you can imagine to have a much longer burn-up. And I think Carlo Rubbia has demonstrated this beautiful possibility of a compensation between the U-233 breeding and captures that are potentially allowing you to extend the burn-up to really extreme values. We're talking about 140, 150 gigawatt day per ton, and this is really a very nice feature of these systems. Okay, I skip a little bit lead. Lead plays a very interesting role as a target, a moderator, heat removal agent, eventually a containment medium, because you have a lot of lead, and it's essentially as good as sodium in terms of transparency to neutrons. Is a capture cross-section here. And one of the drawbacks is corrosion when you get to high temperature, but there's been already quite a bit of R&D on developing material that can withstand corrosion at higher and higher temperature. I think nowadays you can run a system with a temperature of 500 degrees. So all this phenomenology of lead was tested in the ThEC experiment. All this is really very well known. I will not go into that. What I want to say is that this simulation allowed to really calculate the destruction rate of TRU, and essentially a system like the one proposed can destroy 36 kilograms of TRU per terawatt-hour. Just for comparison, PWR produces about 14 kilograms of TRU per terawatt-hour. Now, with the 100 megawatt thermal and a K of 0.98, one can destroy 31.5 kilos in 1 year, which is about 25% of the waste of a PWR, just to put things in perspective. Now, today, the emphasis has clearly shifted toward energy production, mainly because of developing country. The two options are not incompatible, and I think there is no real contradiction between making an ADS that would produce energy and an ADS that would not. And in a system where you recycle the TRUs because they all fission, you can see this that Carlo already showed, where you can really reduce the inventory of radiotoxicity over the long term and just be left with fission fragment radiotoxicity, which after a few hundred years goes essentially to the level of the thorium ore that you use to exploit the system. We're going to hear, I suppose, a lot of discussion on the accelerator, so I put here some of the requirement for such system. A beam power range, I already said, between 1 to 10 megawatt, beam energy 800 MeV or above. If you want to be optimum, that doesn't mean you could not work at 600 MeV. Beam losses are an issue. You have to really minimize irradiation of the accelerator components and of the environment. An impact on that has a major impact on maintenance, so it's a very important point. Reliability, you don't want too many beam trips. You can, if you have a interruption of the beam which are long enough, you have temperature cycle of the fuel that do fatigue and things like that. You want to be able to vary the beam energy. That might be very important if you want to have a system that can adapt its power to renewable energies, for instance. And you want to be energy efficient. And this is something that improves with power. The higher your beam power, the more efficiency you have. And of course, in the end, you want something which is cost effective and not too big and so forth. So the conclusion is that the physics of ADS is entirely known and reliable. Simulation is available. Now, when taking into account the need for safety, waste management, and non-proliferation, thorium in a fast neutron ADS is optimum, as shown by Carlo Rubbia. It is a challenging innovation, but there is no showstopper. There is no reason a demonstrator of significant power cannot be built, and I hope that Hamid will be the first one to do this, or hopefully over not too long time scale with Mira. And it's very important to go to the real system to evaluate the various technological solutions for all the elements of the system. And I think as soon as there is a demonstrator that this would stimulate targeted R&D in a coherent way, hopefully in an international collaboration, as global issues should be faced by global responses. So thank you very much.
Thank you, Jean-Pierre, for this rather comprehensive introduction to ADS. It's time to answer questions now, please.
Hi. I think the fundamental question here is one of philosophy, of values and beliefs.
I'm not qualified for philosophy, for physics maybe.
Yeah.
But
if my core belief is that nuclear fission is physics, then it's pretty normal to have a design philosophy which says that fission is physics, physics is accelerators, and therefore fission must be accelerators.
No,
If, however,
solid state physics is not accelerators.
If, however, my core belief is that nuclear fission is at the interface between physics and chemistry, then I'm going to follow a very different design philosophy. So I'd like to ask actually everybody in this room, what do you believe? What is the true place of nuclear fission in science? And I'd like to ask Jean-Pierre Revol, as a physicist, are you ready to share nuclear fission with the chemists?
Well, for the first question, let me be very clear. I think physics is not a matter of belief. It's a matter of experiments, facts, and so that part is easy for me. For the other thing, everything we do, we publish, it's shared with the community, and not only that, but we welcome international cooperation, and we, as I even mentioned, areas where we need chemists. If you want to make molten lead, for instance, work at 700 degrees, then you need chemists who will help develop material that can withstand corrosion, and therefore I think we need the collaboration not only of people of the world, but also of people from different fields who can all contribute to the project, if that's what you meant.
Thank you. Do we have a question about ADS?
Oh. Hello?
Okay.
Yeah.
Short question. Could you say something about the fuel? What is your proposal in the initial ADS system here? The fuel itself, the rods, okay, the pellets. So that's the first question. Second question is, if you look totally away from the accelerator and only look at the reactor and the core design and the reactor, is there any? How would you compare the core and the reactor to, say, a PWR in terms of the shielding and the complexity of it in itself? But first of all, the fuel. Just describe what it is.
Okay, I'm not a fuel expert, but I think I remember the idea was to have metallic fuel at one point. But I mean, the fuel issue should be also part of the R&D to define what is the best fuel. I think I'm not telling you in detail what is the optimum solution, and this is why we need a prototype to work on all those things. There's a question there. Mm-hmm. Yeah.
Thank you. Jean-Pierre, I was involved with Carlo in the accelerator side. And one of the big trouble that we get in order to have the dialogue between accelerator physics and nuclear reactor physics, it was a definition of minimum trips.
Yeah.
This was one of the key discussions that we got for many, many times. And then, as you remember, Charpak used to say, le mariage de la carpe avec le lapin. Mm-hmm. And in fact, for the nuclear physics people, they don't like at all the word trips. Now, since then, we have done some, we have found some possible solution about trips.
Yes, in fact, I don't want to anticipate on the talks that are going to follow, but this is exactly what I mentioned on my list, and I know speakers like Mondrian are going to address this. I mean, there are ways to minimize trips, and you will see some proposal for that. I think trips are one issue. The other issue is beam losses. You don't want to irradiate. Today, anybody could make a 10 megawatt proton beam. There is no problem, but I could not give you a 10 megawatt proton beam that you could use because you would irradiate the environment and things like that. But there are very good ideas on how to palliate those type of problems, and I suppose we're going to hear that in the next talks.